So hi everyone. Today we have the immense honor of hosting one of the brightest men in mathematics, Professor Alessio Figalli. Professor Alessio Figalli is a renowned Italian mathematician whose groundbreaking work primarily focuses on the calculus of variation and partial differential equations. His exceptional contribution to this field have earned him a numerous prestigious awards and accolades. Throughout his illustrious career, Professor Alessio Figalli has been recognized with several prestigious awards like Picot Vemont Prize in 2012, MS Prize in 2012, Stapantia Medal in 2015, and finally, the prestigious prize is the Fields Medal in 2018. In addition, to these accolades, he was invited speaker at the International Congress of Mathematicians in 2014. His research excellence has also been supported by a European Research Council grant in 2016. We are incredibly grateful to you, Professor Alessio Figalli, for accepting our invitation to joining us today. Your presence is really inspiring, and we are excited to delve into fascinating world of mathematics through your insights and your experience. Thank you, Professor Figalli, for accepting our invitation.
A pleasure. Thanks for having me.
We start by the first question. Can you tell us first about your academic journey and what motivated you to pursue a career and complete your study and the field of mathematics?
Well, it has been a bit of a surprise for me. When I was a student, in school, I didn't know what I wanted to do yet. Mathematics I liked, but I wasn't sure for my university degree. And towards the end of my high school, I discovered a bit the Math Olympiads. And then through the Math Olympiads, I got exposed to these, mathematical games. And also I met many other students who were passionate about mathematics. And then I thought, it looks interesting, it looks cool, it's fun. I liked the challenge, the intellectual challenge. So I decided to try to do mathematics at the university. And then once I was in, I just loved mathematics. I enjoyed very much, going to class, learning new things. And then it just one thing came after the other. I finished bachelor, of course, I went for master, finished master. I just decided to continue doing a PhD. And then from there, I did my academic career, first in France, then in US, now in Switzerland. But let's say it wasn't planned in some way. It was more like I was inside and then things were going well and I just kept going with it.
Okay, and do you have a special story with the mathematics?
Special story. Good question. I think so. For me, one thing that I remember, let's say, was really I wasn't so. For instance, until high school, also when I finished high school after after the summer, I was still struggling in my mind. For instance, what I wanted to do, I wasn't sure I would do mathematics still. I was a bit maybe engineering could be nice as well. Physics, why not? I don't know. I was very confused. Then I just went to try this admission test in Pisa to go to Scuola Normale, which is this school where it's just few students, and then you have this fellowship, and you kind of live there, and it's a very prestigious but also very challenging school. And then I wanted to be admitted. I tried the test, not having much hopes, I must say. I didn't believe I could make it. And then the moment I passed this test, I got so excited. Then I said, no, I want to do mathematics now. And then I arrived to university, and it was a shock because at the beginning it was like totally new to me. I studied classics in high school. So in high school I was doing mostly literature. I was doing Latin, Greek, philosophy. So I had very little knowledge of mathematics. I didn't do any derivatives. I didn't know many concepts. So at the beginning, I was like, oh my god! So now they're gonna kick me out after 1 year. I will do so poorly in the exams that I'm gonna be kicked out. And so all my first year, I struggled just to make sure I was not gonna be kicked out of the school and lose my fellowship. And of course, it was stressful, but then things in the end, with time, you gain confidence and things go better. But then one thing came after the other in the sequel. But I remember like the beginning shocking moment of being faced with university mathematics, where it was like, oh my god, I'm never gonna make it.
It's very nice. So since you were awarded and the Fields Medal in 2018, could you share us some insight about the Fields Medal and your experience receiving it?
Well, that was a huge emotion. So the Fields Medal is given every 4 years in this International Mathematical Congress, and it's a very sometimes mysterious process, because the committee is secret. It's done very beautifully, I think. This committee is secret, so there cannot be any pressure on the committee members, and then they have to get nominations from other institutions, other people, and then they have to do this. The process lasts more than 2 years. I mean, it's a huge process. So to me, it was really, really impressive. I don't know, I would say shocking, when I was contacted. So you don't know anything until the last minute, and then suddenly, boom, they call you. It's it's kind of crazy. At the beginning, I didn't believe it, right? So the president of the International Mathematical Union called me, and I was there shocked on Skype. He told me, "Yeah, we would like to give you the Fields Medal," and I was like, "Oh my god, that cannot be true." It's the kind of things I think. So thinking about prizes, they can put a lot of pressure. So I always never thought about this until probably the last moments, where people started to put this in your head. But if someone had told me about the Fields Medal 10 years before, or even a few years before, I wouldn't say, no way I'm gonna get it. Come on. I mean, it's kind of magical, right? Also, you have, as for every prize, you also have to be lucky in some sense, right? Because in reality, it's a group of people, very experienced, with a lot of knowledge, but still they have to make choices, right? I mean, they have selected few people who cannot deserve it, and then they have to choose in the end of the only 4 who will get it. So it was, it has been for me kind of a big emotion, big moment. And sometimes when I still think it now, I still believe, did I really get it? I don't know. It took me months even to believe it was true, right? And then sometimes it still looks magical. I don't know.
It's a great experience with the Fields Medal. Nice. So you work on several fields, among which calculation of variation and the equation with partial derivative. Could you simplify this concept for us and for people?
So, calculus variation is a very old topic. It was started, I would say, with essentially Euler and Lagrange. So it's really like finding minima in problems. So we always want to find the best solution in some problems. So one of the classical problems is like the brachistochrona. So you want to go from one point to another point. A ball is subject to gravity, and you want to find a shape so that the ball goes from A to B, so from initial point to final point, in the shortest possible time. Or you want to understand what is the shortest route to go to some direction, the quickest way to do something. So it's always about, let's say, minimizing something, or maybe maximizing, depending on how you look at it. But finding minimizers or maximizers of problems where you are looking for the best possible outcome. So this is the calculus of variation, the problem. And then when you have these problems, you have to understand how they look like, right? So the first step is to understand them, these problems, the minimizers, where they exist, first of all. But then you want to understand how they look like. And to do that, you have to write some equations. So these are what we call the Euler-Lagrange equations. So these are equations that usually are satisfied by minimizers. And these sometimes can be ordinary differential equations, like in Newton law. So acceleration equals something, velocity equals something. So you know your particles and you know how it at the speed of the particle at each time. Or it could be more complicated because maybe you are trying to model some more complex phenomenon, like let's say you have a fluid that moves, and then at each point you want to know the velocity of the fluid. And the velocity of the fluid depends on time, but depends on the position of where you are. And so you have an equation for the velocity, which will tell you how the velocity changes in time. But then because there are many variables involved, times and space, you have a lot of, let's say, different so the problem becomes more complicated than just simply when you have acceleration of in Newton laws, and because you have more variables than just one, which is in that case was time. And so you get what we call partial differential equations. So equations where you have a lot of derivatives in multiple variables. And then these questions usually are very challenging because these solutions are not explicit. So solution to PDEs are just not explicit, and the only thing you can try to do is to prove some properties of them, understand them from mathematically. And this is very challenging. It's very important because you want to understand whether the model makes sense. You're always trying to model something physical, and you want to make sure that the PDE that you wrote really matches what you see in observations. And so you are just working just with equations and really trying from that to get something deep out of it. So that's what I do. I have a lot of fun.
It's nice, good. Thank you so much. Also, you have used optimal transport technique to obtain improved version of anisotropic isoperimetric inequality and has obtained several other important results and the stability of functional and geometric inequality. Can you tell us a little bit about the transportation theory and the optimal transport map?
Yeah, so optimal transport is a very classical problem by now. It started more than 200 years ago with Gaspar Monge, and it was really like finding the best way to go from one place to another. So you just essentially, because you want to, the idea is that you want to transport material. So you have, let's say, some material in one location, you want to send it in other locations. Perhaps you have multiple possible targets, and you want to do it in the most efficient way. If you want to think in modern terms, you can think, you have people living in some houses, you know where the houses are built, you know where the offices are, so people have to go to work. And then the question is, what's the best route? What's the best infrastructure you have to build so people can go in the shortest possible time, and so on. So this is optimal transport, transporting objects from one place to another optimally. And essentially, so you are trying to look for there are many formulations of optimal transport, let's say. So there are formulations where you're trying to build this kind of infrastructure. So you're trying to understand a bit how to formulate that. Or there are other formulations where you're just saying, okay, let me play in a different way. So let's say I have bakeries that produce, I don't know, croissants. And then I have coffee shops that need these croissants. And then what you want to do is maybe in the city you will have many bakeries and then you will have many coffee shops. And then you want to decide which bakery will give croissant to which coffee shop. So to minimize the total, let's say, transportation cost. So you're trying to do it, for the wealth of the whole city, you want to minimize the total transportation cost. So you have essentially arrows that go from bakery to a coffee shop. And of course, they will try to do it optimally. So most likely the closest bakery will send material to the closest coffee shop. But, if some bakery does it, perhaps this creates that this coffee shop, it's already now full, it got all the croissant it needed, but perhaps then there was in fact some other bakery in some other part of the city which should have rather sent them croissant to this bakery, because then if you look at the total cost, in fact now that this bakery has to send it so far away in another direction. So what I mean is that it's a global optimization problem. It's not just me going to the closest one, because my choice will influence everything else. So you have this kind of optimization problem. You know, if you have 10 bakeries and 20 coffee shops, it's not super complicated. But if you start to have hundreds, thousands of variables, it gets very complicated. And the optimal map is just the map that tells you who goes where. So which bakery to which coffee shop. It's a map that gives you the destination. And again, if you have few data, everything is easy. If you start to have millions of data, things change. So maybe you will not, at first sight, you say, why do you care about millions? There will be never million bakeries in a city. But, you know, in fact, by now, optimal transport is used in many applications. And one thing people do, for instance, is to use you can use this, for instance, in image processing. And then in image processing, an image is made of pixels, but millions of pixels. And then you want to transport pixels around to maybe adjust your image, change the intensity or whatever. And then you suddenly work with millions of data. And so you have this kind of maps that tells you who goes where, and you want to understand the property of the map. And this is one of the questions on which I've been working on.
Okay, thanks. What is the Monge-Ampere equations, and how did your research impact stability of functional and geometric inequality using optimal transport technique?
So as for we discussed before about calculus of variation, right? So in calculus of variation, what happens is that the minimizer will solve some equation. In optimal transport, is the same. The optimal map minimizes something, is the total transportation cost, and as a consequence of that, will satisfy some equation. And the equation is the Monge-Ampere equation. So the Monge-Ampere equation is the equation that is used to understand optimal maps because they solve such PDE. It's a complicated PDE because it's nonlinear, highly nonlinear. And so I've been working on it a lot, but at the same time, I was interested in how I could use optimal transport, optimal maps to prove something else with them. So because it was very well known since the 90s that you could use optimal transport, for instance, to prove isoperimetric inequalities, to prove other kind of geometric inequalities. So the principle of inequalities is like, so is mixing here I'm mixing two topics, right? So there is optimal transport, and then there is another area of mathematics, which is geometric function inequalities, which is about, you have some space of functions or some space of sets, and you want to minimize something in that situation. It's very general as a topic, right? It's calculus variation. And it turned out that optimal transport could be used as a tool to solve some questions in the calculus of variation. So that was the magic in some sense. So people realized that there was a connection between OT as a problem and calculus of variation, other calculus of variation problems, which had nothing to do with OT. And optimal transport was just a tool in improving this. So it was really coming as a beautiful instrument. And so what I wanted to do was kind of, use optimal transport, push it further, and try to use it to prove new results about geometric and functional inequalities. And that this was really like, for me, I still work on these kind of problems after so many years. This understanding the connection between optimal transport, functional inequality, geometric inequality, how to improve them. So it gets a bit technical, so it's a bit tricky to enter until you see the proof, it's difficult to explain how optimal transport enters in that. It's a bit of magical, it's some chain formulas that you have to see. But it's something that when I saw it first, I was young, I was still a student. I was like, wow, so cool. I would not have expected that.
Okay, thanks. And what is the isoperimetric problem and the plan, and what motivated you to explore and provide a version of this of the anisotropic isoperimetric inequality?
Okay, so the isoperimetric problem in the plane is a very classical problem. You can just formulate in this way. You give me a shape in the plane. So you are in the plane, you give me some shape. Let's say the shape has area 1. So you know the total area of your set in the plane. And you want to minimize the length of the boundary of the domain. So you can try to play with it, like let's draw a triangle of area 1, and you can compute the perimeter. Now let's draw a square of area 1 and compute the perimeter. Let's draw a regular hexagon of area 1, and let's compute the perimeter. You can do this for every polygon, for instance. And what you will realize is that the more sides the polygon has, the smaller the perimeter becomes. And in the limit, as the number of sides goes to infinity, you will get a circle, so a round circle. And in fact, the round circle is the solution to the isoperimetric inequality, because among all possible shapes, not just polygons, but every shape you can think of, the circle, among all shapes which have area 1, will have the least perimeter, so the least length of the boundary. This is the isoperimetric inequality in the plane. And the questions that there are many questions you can ask. So first of all, this problem as an analog in higher dimension, so in 3 dimension, 4 dimensions, and so on. But also, instead of the classical perimeter, the classical length that we think of, where you just measure how long a curve is, there are what we call an isotropic version of it. The idea is that maybe I have a curve in the plane, but the way I measure length, so how long a piece of the boundary is, depends on the orientation of the curve. So if my curve, let's say I draw a curve in the plane xy, if my boundary, so my curve in some part is pointing, I don't know, it's parallel to the x-axis, the length will cost me like 1, like in the usual case. But as the curve bends and it goes more parallel to the y-axis, it's gonna pay 2. So the cost of the length depends on the orientation. So why do you do this? We do this because you can model crystals with that. So shape of crystals come naturally from this kind of anisotropic perimeters, where you don't see anymore a round shape, because now, you know, going in one direction is more expensive than going a different direction, perhaps. And so the final shape will not be round anymore with these anisotropic perimeters. So this is something that people realized more than 100 years ago. And the question is, can you prove these kind of inequalities? And can you understand how stable they are? So what happens if, for instance, I change a bit the setting? So physically, this makes sense, because you can think in this way, like, so the anisotropic problem, the isoperimetric problem is really just about understanding the perimeter, and the perimeter is like the surface tension of your object. So it's about surface energy of your object. So it could be a circle if you're in the plane. If you're in 3 dimensions, you will have a 3-dimensional object, so a ball or a crystal. And then what you're measuring with the perimeter is the surface tension. But perhaps, you know, the object is subject to other forces. There is gravity, there is wind, there is temperature. So there are other forces that will act on your shape. And maybe you want to take this into account. So you will not have only perimeter, but you will have other energies, which will be lower order, small, because the dominant one is the surface, but still they're there. And you want to understand how these other forces influence the shape. Because you see, when you say that I don't know, for the classical perimeter, when you say that the best shape is round, this is only if there is no other force acting on it. Because already, if you play with soap bubbles as a kid, you know, the soap bubbles are round. But if you take a big soap bubble, one can realize that because of gravity, the soap bubble will be a bit more compressed in this direction than in this direction. So it's not going to be exactly round. It will be a bit more compressed here because of gravity. So my study was, how can I prove this mathematically? I can understand this mathematically, these shapes and the effect of forces. And I did it for the classical perimeter and for the anisotropic perimeter using optimal transport.
Okay, it's good. And is there a link between Hadamard manifold and isoperimetric inequality?
Well, you see, the supermetric inequality is a very general question, right? So you have a set in the plane, in 3-dimensional space, on a manifold, so on a curved space, and you fix the area and you want to minimize the length. And on the plane, we know the solution is the circle. On Rn, we know the solution is the sphere. On many manifolds, we have no clue what is the solution. So there is no answer. So there are beautiful conjectures, like conjecture what happens when the curvature is negative, which is the Hadamard conjecture. And the belief is that if if your manifold has some properties, the way it bends goes in some ways, which is bending negatively curved, then in some sense it will the flat case, so Rn will always do better. So the isoperimetric inequality can never beat the one of Rn. So there is kind of so the reality is that if your space is not flat or perfect, right, you see Rn, so flat space or the sphere, there is no way you can characterize minimizers. There is no way, because it's too complex, the space. So you will never know how they look like, but perhaps you can say something about them. And this would be something like, okay, I don't know how they look like, but the area I have to pay, sorry, the perimeter I have to pay relative to the area inside will always be worse than what I would have to pay in the flat case. So in some sense, it's just a comparison. So I don't know how they look like, but they will never do better than what I already see in the flat case. That's the principle of some theorems which are still open. So, well, they're proving some dimensions. So it's known in 2, 3, and 4 dimension, for instance, it's known that if you have negative curvature, then you cannot do better than the Euclidean space. But in higher dimension, it's still open. So there are beautiful mathematical questions about this problem.
Your collaboration with Jacques Serra led to proving the Georg conjecture for boundary reaction term and dimension less than 5 or equal 5. What was the significance of this achievement?
So all these questions about the Georg conjecture come from a parallel. So they come from minimal surfaces. So there are these. So minimal surface is a surface that minimizes the area with fixed boundary conditions. So this is called plateau problem. So you give me a boundary and you try to find the best surface that minimizes the area. And people try to understand the shape of minimal surface since 100+ years. And what people realized over time is that minimal surfaces in low dimensions are very nice, and then in higher dimension you can get problems. So in the minimal surface community, the critical dimension becomes 8. Below 8 dimension, minimal surfaces are smooth. Above, they can have singularities. And in that sense, this is a very deep result about how this surface behave. And then what people try to do, this is the intuition of the Georgi, was to try to find this kind of behavior, dimensional behavior, also in equations, so partial differential equations that resembles to minimal surface. In which sense? In the sense that you have functions now that solve some PDE, but if you take the level set of your functions and you look them from very far away, so you have a function define some space, but then we do what we call a zoom, a sort of zoom out, zoom in. So I just look from very far away my function. From very far away, it looks like a minimal surface. So the level set looks like as a minimal surface should do. And then you ask yourself, okay, I know that minimal surfaces are kind of regular and they have nice estimates in low dimension. Do I have the same for PDEs? So do PDEs that from far away look like minimal surface have the same kind of rigidity properties that minimal surfaces have? So do they inherit that? This is just an intuition that the Georgi had in the 70s, but proving that it's another business. So this led up what is called the Georgi conjecture, and you can formulate that for many class of PDEs coming from different models. So with what we did with Serra was to study some PDEs coming from boundary reaction diffusion, which have the property that when looked from far away, the level sets of the PDE looks like a minimal surface. So you do expect to have this kind of minimal surface behavior. And we managed to prove that in dimension, essentially, I would say, if you think in terms of minimal surface, it would be in dimension 4, which was totally open. It led to a new approach to these kind of questions. Of course, actually, many conjectures here are still open, but it was a beautiful result. I enjoyed a lot working on it. And it's kind of, people are still trying to understand all these connections. It's a very interesting and active area of research.
Okay. Could you provide insights into your work on Hamiltonian Jacobi equation and their connection to weak Kolmogorov Arnold-Domozen theory?
Well, so the KM theory is a very old theory by now. Well, depends how what is old, but it's by now it has a few decades. And it's a theory to understand dynamical systems. So in dynamical systems, you have particles that solve some Hamiltonian equations, and they move, and you try to understand chaotic behavior, for instance, or non-chaotic behaviors of these trajectories in dynamical systems. And there has been a development of this theory, which has become the weak KM theory. So it's a more a soft theory which tries to capture this behavior, but more from a, let's say, PD viewpoint. This has been developed in the 90s. And the Hamilton-Jacobi equations are very much connected to Hamiltonian dynamics. And so there are a lot of questions that you can ask at this level, and this particularly is asking how do solutions to Hamilton-Jacobi equation behave. So again, it's a nonlinear PDE, and you want to kind of prove things about the solution and then connect the behavior of the solution to the dynamic that you see. So it's really like going from PDEs to dynamical systems and connecting the two areas. So this is something I've been working on. I would say, well, I started almost 20 years ago. Time flies. It's a very challenging and beautiful area. So we have been proving some of the open conjecture in the area, although there is still also there a lot to be done. I mean, it's not very easy to explain essentially what they are about, right? But it's really try to connect the two words, PDs and dynamical systems.
It's good. Thank you. First of all, mathematics are just a theory, or there have real world applications.
Well, mathematics, when it was born, it was for real world application. It was to understand the world, describe the nature, describe what happens around us. So mathematics was developed over time more and more because motivated by real world application always. Then with time, of course, mathematicians try to ask also questions which are more for just to understand mathematics by itself. But the reality is that, all the technology we have now, it exists because mathematics exists. So I would say it goes together, right? So mathematics develop and real world application develop, and they go together. So real world application motivates mathematical research, and the mathematical research can be used to create new applications. So I think it's a nice synergy.
There is a relation between these two fields, physics and mathematics, and we can see the application of math and physics, and also the application of physics and math. Yeah. Okay. The world today talk about the artificial intelligence. Is that the mathematics has a role in this area development?
Definitely. So, I mean, artificial intelligence in the end is really optimization problems. Is how to best in this whole AI business. The question is how to best train a neural network, best optimize parameters, best why it works, how stable it is, a model. So when do they do mistakes? Why they do mistakes? And then you can formulate this as a mathematical problem. Of course, it's a very challenging problem because there are a lot of parameters in it. So it's difficult to give like standard mathematical terms, like very universal terms. But you can try to understand. Okay, I have so many parameters in my model, so much computational power. Can I solve this problem? And perhaps mathematics can tell you, no, you cannot. I'm sorry. There are your dimensions. The number of parameters you are trying to use is too small for the problem you want to solve. So there is no point in putting millions of dollars in this project now because just you don't have the computational capacity to do that, or you have to change the problem, or you have to understand that you will never solve it fully. I don't know. So it can really give answers in the deep understanding of why things work or do not work. Of course, then AI, it also goes very fast because it goes fast because of computational power. It goes fast because of really like just moving on very quickly with better models, better training, and so on. But I think if we really want to understand how it works, why it works, when it works, how robust it is, and so on, mathematics will definitely play a huge role in this.
Okay, and do you have an idea about can artificial intelligence solve Riemann hypothesis or P equal MP problem?
I don't think so. I really don't think so. I think it's very far from that now. It's not even able now. So the best models now, they are like bachelor students, essentially good bachelor students, the best trained models which are trained to do mathematics. With time, they will do better. They will do probably better than good bachelor and master students. Okay, but this is still like mathematics that exists and it's very well understood. But to solve these kind of huge problems, you need just totally new ideas. I think I would be very surprised. I mean, the only way you could do it if people already in reality discovered everything needed to solve this problem, just they didn't make connections. So where AI can help is to make connections that people didn't realize existed between different results, different areas. So that would be the only way, right? So that in reality, maybe people already proved everything needed to solve this problem, just they didn't realize that it's already there, but it's in different topics, in different areas, different communities, and they missed something, a connection. That could be it, but I found it very unlikely. But otherwise, I don't think AI will give you new ideas missing to solve these problems. And I think we need new ideas still.
Okay, and what's your advice to students to excel in mathematics?
So, when I started, as a student, I just thought I would never succeed. But not even to become a professor. Just even my first goal was just, finish university with good grades, right? I mean, it was not. I was very, and what helped me was just, train a lot. So, mathematics require constant training. So do a lot of exercise. Every time you study something, you need to do exercise because, mathematics is not like learning by osmosis or just listen to theorems. You need to theorems, you apply them. You understand how they're applied. You really need to make them yours in some sense, right? Something that you use as a tool where you don't think about it anymore after a while, right? It's like now probably once you're an adult, you don't think anymore what is 2 times 3, right? You just know how to do multiplications of some numbers like 2 times 3, right? I mean, but maybe as a child you're there and you start to count and you check. So you have to make yours things, and the same has to go like this, right? With university you have to, but this is only done because you exercise a lot. So you need to exercise a lot, and you need also to realize that mathematics is made of frustration because it's difficult. So there is a frustration, there is a failure because maybe we don't know how to solve exercise, and we just need to. So if we don't know, we have to look at the solution, learn the solution, try again. Maybe we don't know still, look at the solution, understand the solution, try again, and so on until we finally break the pattern and we say, okay, now after 10 times I start to have an idea how to solve something. And then you get confidence, and then you keep going, and then perhaps you can go to much more difficult problems over time, and that's how you improve. So it's really a constant training, but one has to take it in the right way. Also, the failure is part of the training, and one has to take failure as a positive things because it means you are learning. That's the only way to learn, through failure. So that would be my my advice.
Okay, so this is an important advice for students and people who want to study mathematics. So this is I will conclude with this question. A question for people who hate math. Who can they change their mind and this situation?
For how to change their mind. Well, there are people who clearly don't like math, and I can understand. So I don't think everyone needs to like it, right? I mean, some people like math and they don't like other subjects. That's not the point. I think it's not to be. There are people just who got scared by math, and that's I think the problem, right? So over time with schools and just with time, people got scared, and then they just refuse math. It becomes like something. It's not even they don't even approach it. It's not they say I can do it, but they don't like it. It's like I don't want to hear about math. They're scared. They just want it as far away. So that's the problem. And I think it's again because I think there is a wrong perspective about mathematics. So if students don't understand quickly, then professor can be dismissive. Oh, and it doesn't. This student is not good. And then once, I think that I'm not good, I will never be good, right? Already the professor told me I'm not good. I give up, right? Then, which is something that we don't see in other areas. So no one will tell you, oh, you're not good in history. And then, oh, okay, then I stopped learning history, right? I mean, you just didn't study, right? And with mathematics, there is judgment, and that's the real problem. So I think what we need is to make sure that students, don't get judged and don't get this. A professor should not tell them, "Oh, you're not good at." That's a very wrong statement. I don't think anyone can say who is good or who is not good. Just students have to keep doing their best and learn as much as is required by the curriculum. And of course, we need to make it will be good in school to make math also a bit more exciting and more attractive, perhaps with more examples, more applications, a bit more cool problems sometimes. But the point is not to make people be scared. Then the rest, if they don't like mathematics after they've done it for many years, okay, well, we don't like everything in life. So that's life.
Okay, we pass now and to the followers' questions. We start by Saeed Kamam. Could you ask him what are the biggest open question now in the field of partial differential equations?
So, okay, there are many. There is one, the famous one is is in the same realm, what you discussed before when you asked, can AI solve Riemann hypothesis and P equal in P, right? So in the PDEs, there is an analog of these millennium problems, which is the Navier-Stokes equation. So it's a system of equations. It's about fluid mechanics. Again, fluids. You're modeling a fluid which is incompressible and viscous, and you want to understand how the solution behave. In particular, the big question is, can solution become irregular? So you start from a very nice fluid which is moving very nicely, very smoothly, nothing bad happens, and then suddenly after time, the fluid starts to accelerate and create very fast vortices or stuff like that. And I think the question by itself is beautiful mathematically, but also most of these questions are not only about the question itself, but about the mathematics you will need to develop to answer this question. This is also very fundamental. So this is probably one of the most famous one, Navier-Stokes. But in reality, so PD is huge. So the point is that PD is huge. So this is Navier-Stokes about the fluid community. I work more in elliptic PDEs. So these are equations of other sorts, and I work particularly in free boundary problems. So these are equations where you have some PDE and some interface. So a classical example is ice in water. So you drop ice inside water, and then the ice will melt. And so you have the PDE describing the evolution of temperature inside the water, plus the fact that the boundary moves because the ice is melting. And many fundamental questions there are totally open. You go to there are people doing dispersive, there are people doing general relativity PDEs, there are people doing many kind of PDEs, Boltzmann equation, still big open problem. So there are many fundamental equations of mathematics and physics which are totally understood. So I don't think there is the biggest open question. There are just, depending on your community, you will have some Graal problems that everyone wants to solve, and usually are very challenging, and then one tries to improve the knowledge over time and do his best, his or her best.
Okay. We pass to the next question. How do you approach the problem of existence and the uniqueness of solution of nonlinear partial differential equations?
That's a challenging question because it very depends on the PDE. So given a nonlinear PDE, you need to understand. So first of all, existence. That's the first question, right? So you have an equation. You want to understand, does a solution exist? You expect it to exist if the question comes from some physical consideration because it's describing some physical phenomenon, but perhaps you need conditions, boundary conditions. So you need something to make existence available. There are by now a lot of methods. Some are called continuity methods. So we prove a priori estimates, so try to understand whether solutions are smooth in some way. So you kind of play with the equation even before knowing that the solution exists, and then a posteriori you prove that it exists. So in the one classical reference is, I would say, the old by now standard book, Gilbert Runiger book on elliptic PDEs, where it shows how to solve some elliptic PDEs by this method called continuity method. And for instance, I wrote a book on Monge-Ampere, and I showed, I mean, it was not new, I mean, it's just a standard strategy how to solve Monge-Ampere, either by continuity method or by some, first you find some weak solutions and then you prove that weak solutions are smooth. The uniqueness, again, that's very much part of the problem. For many equations, we don't know how to prove uniqueness. So it's still a big open problem for some PDEs. For other PDEs, maybe you just have, it depends a lot also of whether they're scalar or vectorial, right? So if your unknown is a function or it's a vector like velocity field. But if it's a scalar, sometimes you have what we call maximum principle that tells you that two solutions of a PDE, they cannot cross. So if one is above the other, let's say on the boundary of your domain, then they have to remain orderly inside, and then once you prove uniqueness. If maximum principle fails, sometimes you just don't have uniqueness, and then in fact you discover that there is no reason to have uniqueness. I mean, even very simple ODEs don't have uniqueness. Depending, I mean, it's all a matter of boundary. I mean, it's because there's always a coupling. There is the equation, and there is the condition you put on the boundary of your domain. And so they're usually related, the two things. You cannot just look at the PD itself. You also have to look at what you're imposing as boundary condition if you want to prove existence and uniqueness. So it's a very general question and very challenging.
This question, I like mathematics, but my knowledge about this is limit. I would like to be able and to understand complex and advanced mathematics. Do you have?
Yeah. Well, I mean, of course, some people. All right. If young people, of course, if they want to learn mathematics, the best is to study it at university. For people who are more like, they like mathematics, but they didn't have a chance before to study it. By now, I would say, so it's very difficult to go to complex and advanced mathematics because it requires really a lot of training. So either one decides to study, I mean, just as a hobby, to learn a degree in mathematics, which is not an easy commitment. But otherwise, there are now, a lot of sources online, like YouTube, and many people just vulgarize mathematics. It's difficult to go to advanced mathematics, but there is a lot of beautiful mathematics that is explained because it's more elementary. And also, it doesn't, I mean, mathematics is very vast. So I do PDEs, but there is probability, there is number theory, there are many other areas. And so some areas can also be are more accessible, so especially some problems are easier to explain and to understand. So I think it's my advice would be to use a lot of the online resources available if one just wants to understand more about mathematics and learn more about mathematics to get exposed to beautiful theorems. I'm not sure. Do you hear me now? Because I don't hear you. You hear me?
You hear me? You hear me now?
Okay, now I hear you. Okay, good.
Okay.
I read the question below. I mean, the importance of ideas in the theorem. So there are many theorems in mathematics. So this is about. It really depends what you are trying to do in PDEs. So for some areas of PDEs, there is no need of these theorems. So like, for instance, what I do scalar PDEs on a REN, this is not connected at all to ideas in this theorem. Same if you do fluid mechanics, there is nothing there. So what I mean is mathematics is huge, and the PDEs is a huge field. So sometimes, theorems like coming from, index theorems and things also depends whether you're working in which framework you're working. You working perhaps in a nonlinear setting. You work so like I work on usually on a Rman flat space. If you work on manifolds, perhaps the manifold influence the space of solutions of a PDE because the topology can influence the solution of the PDE and so on. So there is no so some theorems. I mean, what you're mentioning is a very famous and profound theorem, but it only influences a certain area of mathematics, which is not the research in PDEs overall. It's just a part of mathematics specific. So the point is that mathematics is huge and the techniques are very different area from area. So in reality, we just it's very difficult to connect these area techniques just because they don't work usually. So what the techniques we use in some fields of PDEs are just totally wrong in other areas. They just don't give you anything. They don't work at all. And so that's also why it's so rich. There is so much to do because we cannot just export techniques. It's very it's a very vast.
What's your approach for linear flow and geometric analysis?
Well, geometric analysis, it's this famous, it's an area of PDs where you and analysis and is it really the interface of analysis and geometry, right? It's really, for instance, the most famous flow is Ricci flow. In the last years it became very famous because of the Poincaré conjecture. So you have a surface and you evolve it under some PDs. Or another famous one is Minkowski flow. So you evolve it under some equation, but it's geometric now. So it's not the temperature moving, like the heat equation, so the temperature of your domain moving, but it's like you have a surface and the surface deforms in time according to some PD. So usually to understand these flows, to understand the properties, you already need to know basic PDE theory first. And then you can go to this geometric version of them. I don't think there is a universal approach. Usually people would start to work on geometric analysis, usually during their master or the PhD. Then they start to get exposed to these two papers on these topics. There are also by now reference survey, lecture notes, many lecture notes. And then there one just needs to study them, but also redo the computation themselves, because these are one needs. It's again very much connected to what I said before, right? It's like things have to become automatic. It's like 2 times 3 is 6. It's automatic. You don't have to think about it. And then in geometric analysis, when you work on flows, there are some computation that you do over and over and over, and you have to make them yours. So to learn these kind of things, it's study, but at the same time as you read, try to redo computation yourself and do them so many times that after a while you really understood them, that you can reproduce them without thinking. And that's how you have this background to then go and prove new stuff. But you need to have solid basis. But this is very general, right?
I will take two last questions. So what I can no, I think this is, I chose this. Are there any intersection points between the differential partial differential equations and coherent fields described by Serre?
Again, okay, here we're going really at the so Jean-Pierre Serre was not a PD person. He's not a PD person. Of course, there is so the kind of mathematics that was developed, I would say, at that time with Serre. Serre is a mathematician who's been doing amazing work since the 1950s. Was very different from now, I would say. So mathematics has become way more specialized. At the very beginning, there was a lot of intersections. There was a lot of the idea also of very general theories. So people hope to get general theorems exist, even for nonlinear PDs. They wanted to have a unique theorem that proves existence and uniqueness to PDs. And then with time, people just realized that it doesn't work. And the more you want to work on very problems who come from real life, fluids, free boundaries, whatever, general relativity, you need very different techniques. And so by now, I would say that the PD community is very specialized, and this kind of to be honest, so I don't know the answer to this question, but I don't see also an obvious answer to this question, because in some sense, of course, there was always this idea in more generally in mathematics, to do very general theories, but especially for PDEs, it doesn't work. So for PDEs, it's really like problem dependent. We have developed now a bunch of techniques, a lot of tools, but they're very specific to some areas, and that's the way to go.
Okay. The last question: how to use theory of the optimal to give a partial solution of Navier-Stokes equations?
Oh, well, if I knew, I would be very happy. I don't think there is anything, right? So far, this is not there is no connection between the two. So optimal transport has been used to study isoperimetric problems. It has been used for studying some equation coming from meteorology, but there is no connection to real connection between optimal transport and Navier-Stokes. So they just two words, and it would be cool if there was a connection, but I never heard of it.
Okay, thank you so much. As we wrap this live session, I want to express my gratitude to you. Your engagement and your enthusiasm have made this experience truly special. Thank you for joining us today. Thank you, Professor Alessio Figalli.
Thanks for having me. A pleasure.
Thank you so much.
Thank you.